This is a lesson on the basics of circuits and circuit analysis in a unit on circuits. Let's go over the basics of circuits, what components build a circuit. The main function of a circuit is to have a current go through it. And I covered basics of current in a prior lesson. To highlight, circuits must be closed for the current to flow. Charges move according to electric potential, so that's why we're interested in voltage. And current will always follow the path of least resistance. You may see this in problems where a current has an option to flow through a resistor or flow through just a wire, and it will always flow through just a wire because a wire has no resistance. Okay, so watch out. That is true in real life as well. You may think about lightning. Lightning will always take the path of least resistance across the sky. Finally, the last consideration for current is the direction of conventional current, which is the direction of positive charge flow. And like I said in that lesson, if you have feelings about this, I don't blame you. Negative charges are the ones that flow, but for conventional current, when I draw current, I will always be drawing the direction of positive charge flow. When it asks you for direction of current flow through a branch, it will be the direction of positive flow. So watch out for that when you get there. Like I said up here, in order to have current, we need to have an electric potential difference or a voltage. So there will always be a voltage supply in a basic circuit. It provides a potential difference for current to flow, and multiple supplies can be in one circuit. It may freak you out to kind of see that while we do circuit analysis, so I've chosen some problems where you will see multiple batteries. And when we're looking at batteries, there's a couple of symbols that we can use. The easiest one is just a short plate and a long plate. And the long plate is the positive side and the short plate is the negative side. So when you think about batteries, there's a positive and negative. And so current, when you connect a circuit, current will always flow from the positive side to the negative side. Okay, that's the direction of positive charge flow. Another battery symbol is with multiple plates, and you may see that in simple circuits as we do those. So circuit elements. What are the other circuit elements? Of course, we're going to have a voltage supply. We're going to need wires, which we just designate with a line. That will be a wire. A resistor has the symbol like this and connected to a wire. I just do a bunch of wiggles up and down, and that makes a resistor. A capacitor, we know, is parallel plate. So you will draw it with two parallel plates that are equal length, as opposed to a battery that definitely has a long plate and a short plate. So with capacitors, the positive and negative will depend on the current going through that. And I'll show you how to do that in a little bit. An inductor, when we get to magnetism, when you get through magnetism, you know that an inductor, it looks like a spring. And that's sort of what it is. It's a coil of wire. And so that's what an inductor is. This is an L, a C, and an R. This is V for voltage. Wires are not labeled ever unless they're labeled like wire A. They may label it in that way. Finally, a switch is a place in a wire where you can create a break. Okay, and so you can close that break, and they often have dots on both sides, and it may be called like an S, or if you have multiple ones, they'll call it S1 and S2 maybe, or switch A and switch B, but typically S is used for a switch just so you recognize that it's a switch. When we look at circuits, we will also be focusing on branches and junctions. Branches have a current each, and junctions is a place in wires where we have multiple wires come together. And I'll talk more about these as we go along, but I just wanted to give an overview here of all the basic circuit elements, what we're going to be looking at. As we look at voltage through resistors, we'll start circuit analysis with just looking at resistors. We're going to remember Ohm's law here, that the voltage is related to the current and the resistance through that resistor. So keep this relationship in mind as we move towards circuit analysis. I wanted to dive deeper into voltage supplies just for a second, and you can see here that I have a picture of the more complicated battery, which is fine. When it comes to terminology, I see several terms in there, and I can see how this could be confusing for people learning this material. So that's why I'm going over this. A battery is the same to me as a voltage source, a voltage supply, and all of these things supply a terminal voltage. Okay, so these are sort of all, when you see that number next to a battery, they might say a battery is 9 volts. That's what they're talking about. So all of these are approximately the same to me in concept in my head, and the biggest thing that all of these do is provide an electromotive force, and we're going to be looking at DC circuits, direct current circuits, where the current only goes in one direction. So in this circuit up here, I'll label the positive and negative plate of the battery, and I know current will flow in a clockwise fashion around in that circuit from positive to negative, and it will always flow in that direction based on the battery being there and supplying that potential difference. So that's what the electromotive force is. All of these things supply electromotive force, and an electromotive force is a maximum potential difference between the terminals of a battery when no current is flowing. So it may be like a 9-volt battery. Okay, so that is the electromotive force, and we call that battery is able to provide that electromotive force. A terminal voltage is the voltage that the battery delivers. So if you see that terminology, you're aware of what that is. One thing I wanted to cover here was the difference between an ideal battery and a real battery. In circuits, when you look at a circuit like this one over here, we're going to assume that this is an ideal battery. An ideal battery maintains a constant potential difference throughout time. Okay, so if you're doing circuit analysis, you're never worried about that 9-volt battery being a different voltage. Or that 9-volt battery not delivering exactly 9 volts because of its limitations. So when we think about the limitations, we think about a real battery. So here is the picture of a real battery over here, and it is modeled by some ideal battery plus some internal resistance. Okay, so this is a real battery, and the internal resistance, this little r here, is what makes it an ideal. So it might say that this is the 9-volt battery, but when we attach a current to it, when we get a current flowing through here, this resistor isn't receiving all of the 9 volts. There's some other resistor that's consuming some of that voltage. Okay, so that's the bigger ideas on voltage supplies, how we get voltage supplies, symbolize them, and think about them in the circuit. The next topic here is how to measure these things. Now that we have a circuit and we have a current flowing through it, we're interested in quantities in that circuit, namely the voltage and also the current. So the voltage difference, when we look at voltage, we're always looking at voltage differences. You may just read the instrument as volts, but obviously this is a voltage difference. We need to have a voltage difference in order for charges to move and current to flow. So the way to measure a voltage difference in a circuit is to use a voltmeter. You might not be surprised that you measure volts with a voltmeter. And you put that voltmeter in parallel, what we call in parallel, with the section of current to measure the voltage across. So if I have my voltmeter here, and I'll just put a V here, if I wanted to measure the voltage over this battery, I would connect it in parallel, which means that I would put it, and you can see why we connected in parallel is because these two lines are parallel to one another, and I would measure the voltage from one side of the battery to the other with a voltmeter. Okay, I could do that with a resistor too. If I put a voltmeter over here, and let me draw this in here, we'll go like this. If I put a voltmeter over here, I would get the voltage over this resistor. This would measure the voltage over the battery. Ideally, both of these would be equal to one another, but real life happens. So you may see some different measurements in lab. Okay, so that's how you measure the voltage. A final note about voltage is that if you measure a positive voltage, that's a gain in voltage, often you will have two different color probes. You will have a red probe. Typically, you put the red probe there and the black probe on the back side. The black probe is typically ground. And so when you have ground, you would measure that as 0 volts. And so the red, when you measure the voltage difference over here, you would get a positive whatever it is. Positive, let's say 9 volts. That's a 9-volt battery. You would get positive 9 volts. If you switch the directionality, if you switch the red and the black, that will just change the sign of the voltage. Because now you're saying this is 0. What's the voltage compared to that? So if I make this side 0 voltage, then obviously the back side of the battery is going to be measured relative to that point, and it is negative 9 volts of potential difference from that 0 volts. So this is a loss in voltage. So you still get a 9-volt gain. Notice you still get a 9-volt gain over that battery when you move in the direction of the current. So that's how you would interpret a negative sign in a circuit. To measure current, you connect an ammeter, so that's what measures amps, is an ammeter, in series. So we have in series versus in parallel. So in parallel, you can see these two things are parallel. In series means we're actually going to take the ammeter, so here's an ammeter, and we're going to connect it like this. And we're going to get rid of this piece of wire, okay, so that the current now must flow through the ammeter in order to get to the resistor. And then the ammeter is then able to measure the current through that wire because it's connected in series. Current is through. It is a value, whereas voltage is a potential difference. So we have to choose 2 points on a circuit in order to measure a potential difference. But if we want to measure this current, we just put it in the wire, in whatever path that current is that we want to measure. Finally, you may get a question about this. How do you measure resistance? You connect an ohm meter. Remember, resistance is in ohms, so you may not be surprised that we use an ohm meter to measure resistance. You put it in parallel with the resistor of interest when no current is flowing. Okay, so there's an internal current and voltage, and the instrument, whatever you're doing, uses Ohm's law to calculate the resistance equals V over I. These are known values in the instrument, and it can measure the R. So you don't want to have any external voltage or current. So you would disconnect the resistor and then put the ohm meter in here, and then that would be the way to measure the resistance, is without the battery being on or attached or whatever. Okay, so it would be an open circuit somehow. One last thing about wires before I leave this slide, because sometimes they'll ask some weird questions in here. They may point some points on here, and let's put point A, point B, point C, point D on here. They might ask you the potential difference, like which one is higher, A or B? The voltage at A or the voltage at B. And what I'm going to note here is, like, if we did the voltage of A to the voltage of D, you already know that A is going to have a higher potential of D because that's what is making the current flow, right? That's what's making the current flow. But when you choose different points, then that's really asking, do you understand how a circuit works? So when you have 2 points that are along the same wire, all of those points along that wire it's a conductor. They're all at the same potential. Those charges have 0 resistance of moving in that wire. So if it's 0 volts over here, it'll be 0 volts over here as well. The current's going to flow freely from A to B, and the potential at A is equal to the potential at B. Only when we get this potential difference going on, when we get a circuit element in here, either giving a rise of potential or a drop in potential, do we get a potential rise or drop, right? So I would say the potential of B is going to be greater than the potential at C because this resistor is in here. We can see that C is connected to the back side of the battery, and so all points along the bottom side of this circuit is going to have negative 9 volts. That's just if we put the voltmeter in that direction. It would be -9 volts. So watch out for those questions as you move through any homework. All right, now that we've developed some basics and essentials for building circuits, measuring circuits, thinking about how circuits work, let's go and apply the fundamental concepts in physics that determine what's going on in a circuit, right? This will be interesting. These are referred to as Kirchhoff's rules after Kirchhoff. It's based on two principles here. The first is conservation of charge, which is one of the fundamental in the universe. Charge cannot be created or destroyed randomly for no reason, okay? So this is where we get the junction rule. This is what we call Kirchhoff's junction rule. All currents into a junction must add to all currents out of a junction. Okay, so whatever charge goes in must go out somehow. It must all be accounted for. And so that's what you see here. The sum, this is a Greek letter sigma. And if you've done calculus, you're familiar with this term. It's a sum. You just sum it up. All of the current in to a junction has to equal all of the current out of a junction. If we have a really basic circuit, we only have one wire and there's one current in here. There's only one current in here. But when I look at this circuit over here, and this is where I'm going to talk about branches, we can see that the current can be thought of to leave the battery. That's how I think about it. The battery kind of pushes the current around and it'll come back into the backside of the battery. So we can call this I battery, okay? I battery gets to this junction and I battery will split up. It will always split up into what we can let's call this I top and I middle, okay? And maybe this is I bottom instead of I battery, okay? So when I write this out in terms of Kirchhoff's junction rule, I would get I from the bottom on the battery has to equal I top plus I middle. That must be true. Whatever current goes into this junction adds up to whatever current's going out of the junction. We can also look at the junction over on the other side. I'll call this junction A. If I call this junction B over here, we can see I top is flowing into it, and they add up together to equal I bottom or I battery. Okay, so that's the Kirchhoff's junction rule. Pretty easy to apply. If you have more branches and more branches, you may have multiple equations to relate your currents. But for simple circuits, usually it's one. For more complex circuits, you can have more than one junction rule. You would just choose another junction and include whatever currents are going in and out of that junction. The next concept, the big principle that's used for circuit analysis, is conservation of energy. Okay, so when we think about the battery, it's applying a potential difference. There's an electric potential energy, QV, in there for all the charges. Okay, and we'll get to the power delivered by a circuit with resistors. But that's how we think about it, is conservation of energy. There was voltage in that term, right? Voltage. So we're going to say that all the voltage drops and all the voltage rises around a loop. We have to choose a complete loop in a circuit must be 0. So the net, the sum of the voltages around that loop equals 0. And that will be an equation that you will use over and over again. And often that's what you're tested on, is can you identify a correct loop in a circuit. So when I look at this circuit, there are several loops that I could do. And the easiest one might be just to go around the outside. And when I think about that, I think about, and notice that I closed the loop. It's a closed loop somehow. And I chose the direction of the current. That's the easiest way to do that. What I see going on in that loop and how we can rationalize, oh yeah, that equals 0, it should equal 0, is that we have a battery voltage here, 9 volts. Over on the other side, we're at the negative plate of the battery, the only battery in the circuit, so we know that should be 0 volts. Current will flow from high to low potential. The conventional current will flow from high to low potential. So when I go around this loop, I think about all the voltage drops and voltage rises along that loop. The first circuit element I get to is the battery, and I know it's going to supply a 9-volt rise, a rise of 9 volts across that battery in this direction, from negative to positive. When I get to the resistor, though, I know the voltage across the resistor is V equals IR, and it's a drop. I will be losing potential, right? The resistor is what's kind of causing things to slow down, right? It's providing the resistance to the current, and there will be a drop over that resistor. And if I go around in the circuit, I can see that I get V bat minus V across the resistor has to equal 0. And so 9 minus 9 equals 0. So that resistor is getting 9 volts. This is a parallel circuit, and that should make sense for us. You could go in the opposite direction on loops, but then notice that if I go in the opposite direction on this loop in that direction, I would get a negative across the battery and a rise across the resistor, and I would get the same equation. It's just the same equation. So it doesn't matter which direction you do these loops, just stay consistent in your signs and in your loop as you go through it. You can see with this circuit that there are multiple loops. So another one would be this one right here, the bottom loop, I would call that. And then a third loop would be maybe the top loop here. So there's 3 loops here. So you will apply this loop equation multiple times in a circuit in order to relate the different quantities. So Kirchhoff's rules are used to analyze any circuit, simple or complex. As you move into more complex upper division classes, you will see that these are, because they're the fundamental concepts in the whole cosmos, right? Conservation of charge and conservation of energy. These are the determining principles, and these are used with all circuits. It's especially useful when elements cannot be reduced to equivalent ones. So we can find equivalent resistance, and we can find equivalent capacitance, and we can find the impedance for a circuit. And you will see in all of those situations, often the easiest way to relate the voltages of the different elements, especially in mixed element circuits, is with Kirchhoff voltage rule. And then that would relate the voltage across all of the elements regardless of how they contribute to the current of the circuit. So I know this is maybe a little bit over your head at the top of as we go into simple circuits, but maybe something you can remember as we head that direction towards mixed circuit element circuits. So I put together a strategy, and I've been teaching this for years, and I'm pretty confident in how to teach this, and your book will introduce this as well. There's a method for analyzing circuits. Circuits are a system of logic, and when you analyze a circuit, you're analyzing a system of logic, and it will be consistent every time. So there should be no surprise that you can have an approach, some sort of strategy consistently to apply circuits. And I encourage you to remember these steps and do them every time to help you with your circuit analysis. The first thing to be done with circuits is to assign currents. Currents is the reason why circuits exist. We want to get a certain effect on a current or communicate information with currents, etc. So what happens is we assign one current for each branch in a circuit. And again, there's a terminology here, a branch. A branch is a single piece of wire, and there's only one. If you think about this in terms of like hoses in a garden, there's only one stream of water through each hose. You can have multiple hoses and they connect at junctions, but between junctions there's a single piece of wire which may have circuit elements, but there's one current in that branch between junctions, okay? If this is not already done for you, often you will see on multiple choice or exam problems, you will see that homework problems also will have currents already assigned in branches, but if this is not done already, you will need to assign one current per branch. Something students struggle with initially is which direction to assign the current. And what I'm going to tell you is that there is no wrong direction. If you do all the algebra and you stay consistent within that logic that you set up, if you get a negative sign, that just means you picked the wrong direction of the current. But for me, this is like picking the wrong direction for a coordinate system. It's a coordinate system. As long as you're consistent within that coordinate system, you can get a negative sign and just interpret it as the other direction. So when you assign currents, there's no wrong direction, but you can reason according to the batteries. And you saw me do that on the previous slide. Which direction do these currents flow? Well, I went from the positive plate, and it made sense to me that the current would flow from high potential to low potential. And so that was what determined the direction. That's how I knew which direction to put the current. If you're not sure, if there's a situation where there's multiple batteries or you just were kind of sloppy and you get a negative sign, it's okay. Don't worry about it. You just know that the current actually goes in the other direction in that branch. Once you get the currents assigned, one for each branch, you can assign positive and negatives to each circuit element according to the direction of the current. That's why you need to assign the direction of the current. You need to do step 1 before you do step 2. That direction of the current is going to determine the direction of the positive and negative signs, right? Because on the prior slide, I talked about the resistance being lost over this resistor. You can see that there's potential lost over this resistor. I chose the current in this direction over the resistor, and voltage will be lost, right? This is the 9-volt side of the resistor, and this is the 0-volt side of the resistor. And so I put a plus sign on this side and a negative side on this side, and that tells me there's a voltage loss over that resistor. If I had accidentally chosen the wrong direction, if I put the current in this direction, my signs would change, because then I'm saying that this is the high side, right? If current flows in this direction, this is the high side and this is the low side. So that's why we would change the directionality of those signs, because now this would be the high side of the resistor and this would be the low side. If I solved this equation with numbers or whatever, I would get that the current is a negative value in this branch because I picked the wrong direction, and I would know instead that would flow from left to right rather than right to left. Okay, so assign the direction of your currents as mindfully as possible, and then assign a positive and negative to each one of your circuit elements. Once you get those two things done, you're ready to apply Kirchhoff's rules. The first one that I do, because it's just one equation, usually you can relate the currents in the circuit with just one current equation. So currents into a junction equals currents out of a junction. And then apply Kirchhoff's loop rule, and you saw that one circuit, there's multiple loops you can choose as many times as needed in order to solve the problem. You may look at the problem and you may have one unknown, and then all you need is one equation. You just have to match the number of equations to the number of unknowns. And remember that you already have one equation up here. There's one equation up here relating the currents. And then also you can get as many times as needed here in order to get your number of unknowns. So if you have 2 unknowns, you would need 2 equations. If you had 3 unknowns, you would have 3 equations. So you'd have one equation from the currents, and then you could get 2 equations by doing 2 different loops. Okay, they have to be different loops. And then you would have enough equations to solve 3 unknowns with a 3 equation system. Okay, again, we're going to remember that Ohm's law relates the currents to the voltages, right? I have currents here and voltages here. I can use Ohm's law in order to relate them. So now that I've laid all that out for you, let's practice some circuit analysis on a circuit. And again, here's the 2 parallel resistors. I call them R1 and R2, and we have the voltage from a battery. I am going to go ahead and put what I can do on here. I don't even need to know anything in the problem going on in order to assign one current for a branch and assign positive and negatives to each circuit. So you may want to pause for a second and see what you would do and then check against mine. So when I look at this circuit, I would get a plus side here and a minus side, and I always start with the battery. Those tell me the plus and minus, and that kind of tells me which direction the current will go in this side. And so I'm doing step 1 here, assign one current per branch, and we did that before. I'm going to call this I1 up here because this is the current through R1. All right, and I1 flows through this whole branch. So this is a branch up here. right? From junction to junction is a branch. Okay, so I1 has its own branch. I2 has its own branch as well. I called it I2 because it goes through R2. I1 and I2, they branch apart at this junction and come back together at this junction, and they form I through the battery. And so this is I battery here, and this is I battery here. One thing that I see students think is that there's no current over here. But I think of it current in terms of a bunch of charges, right? The wires just have a continuous bunch of charges right next to each other. So when you apply a potential difference here, if I have a charge and a charge, they're like people in a hallway. If one starts moving and you have a whole row of them all the way around, if there's charges over here, they start moving as well. It's just a whole line of charges moving, and so you will have current on both sides of this battery. And a current is constant through each branch. So I2 flows constantly through this whole branch. Whatever you'd measure the current here before the resistor, it'd be the same after the resistor. Same for the battery, same for this resistor. Okay, and I assign positive and negatives to each circuit element. I'm going to assign these in red so we can maybe see these a little bit easier on the problem here. So because I2 flows from left to right in this middle branch here, this must be the high voltage side of the battery, and this will be the low voltage side of the battery. So voltage will be lost in this direction. The same for the top one here. You can see in the top branch, this is the high side, this is the low side. So let me get rid of these charges because I want to use the blue color here. Read the problem and get some loops going. I have a junction rule, but I'm going to see what information I'm given in the problem first. It says the terminal voltage for the battery in the circuit shown is 12 volts. Okay, so I have the battery is 12 volts, and I'll write that over here. V battery equals 12 volts. Determine the current and voltage over each resistor. R1 is 5 and R2 is 8. Okay, so R1 equals 5 ohm and R2 equals 8 ohm. So I'm going to just hold on to those numbers. So I know the resistances and the battery. I don't know any currents. They don't tell me any currents in here. It says determine the current and voltage over each resistor. What is the current delivered by the battery? Okay, so I'm going to know if I find I1 and I2, I can find IB. That won't be a hard thing to do. And that's because of this. Apply Kirchhoff's junction rule, IN equals IL. So if I call this junction A, at junction A, I have I from the battery coming in, and I have I1 plus I2 going out. And that is the Kirchhoff's junction rule right there. So that's one equation I have, and I got that from looking at that junction A. Okay, so I still need to figure out currents. If I figure out currents, I know the voltage over a resistor equals IR. So like V1 is I1 R1, and V2 is I2 R2. So if I want to find the voltage over the resistors, I know the resistances, but I would have to find the current. So those will be my unknowns then. These are my unknowns, I1 and I2, and I'm going to notice that I have three unknowns. I don't know I1 and I don't know I2, and I also don't know I from the battery. None of those are knowns. Okay, so that means I need to shoot for 3 equations overall, and that's okay because I have a couple of loops I can do in this problem. Let's do a green loop. Let's do a green loop. Let's do this one here. We'll do the bottom. Okay, and I just chose clockwise because I often choose clockwise. It doesn't matter. If you went in the opposite direction, you would just have negative signs rather than positive signs. And let's call this loop 1. So for loop 1, I'll put this over here. For loop 1, I'm going to go around and apply Kirchhoff's loop rule. The sum of the voltage, the sum of the rises, and the sum of the drops equals 0. So when I go around this loop, I see I have only 2 circuit elements, the battery and R2. So when I go around here, I would get the voltage from the battery. I get a rise in this direction from the battery, and then a loss, a drop over that resistor. So I'm going to put minus V2 equals 0. Okay, so that's for that loop. That's all that's going on in that loop. And I also wrote down what I know about V2. V2 is I2 R2. So I can write in here V across the battery equals I2 R2. And it seems like I can solve for I2 right away. I2 equals the voltage across the battery divided by R2. Okay, so the voltage across the battery is 12 volts and the R2 is 8. And so very easily I get I2 equals 1.5 amps. Super easy. So then V2 has to equal that times R2. So I can take 1.5 times the R2, which is 8, which is 12 volts. This makes sense to me because when I do this loop, there's only 2 circuit elements. So this resistor is getting all of the, how I think about it, getting all of the voltage from the battery. Let's choose a different loop. I still don't know I battery, so let's choose a different loop to find I2. Let's do something you might not expect to do. I anticipate that you might want to do like a loop around the outer, but what I'm going to do is choose a loop around the top here. Okay, so I'm going to call this loop 2, and I'm going to do some Kirchhoff's loop rule for loop 2. And I'm doing this because you don't have to include a battery in a loop at all. That's not a rule here. It just says any loop you choose has to be 0. So I can choose a loop with just resistors. What I'm going to do is follow the direction of that loop and follow the signs that I've assigned on those circuit elements in that loop. So I will, in this direction, the clockwise direction, I see over R2, I'm getting a rise in voltage. So I'm going to put plus V2. I go around, the next circuit element I get to is R1, and it is a drop. So I'll go minus V1, and that has to equal 0, okay, because there's no other circuit elements in that loop. And what I see is that V2 equals V1. V2 I know. V2 is 12 volts. I solve for that down here. V1, I wrote out the expression, is I1 R1, and I can solve for I1. I1 equals 12 divided by R1, which is 5, which is 2.4 amps. 2.4 amps. Okay. Once I get that, I can go back and say V1 equals I1 R1, so I get 2.4. Which is I1, times R1, which is 5, and you may note again that this is also 12 volts. Okay, so this resistor we can see is connected in parallel with the battery, and that makes sense to us. Okay, so we solved A. Determine the current and voltage over each resistor. So voltage over, you may see voltage dissipated. I don't agree with that terminology. Energy is dissipated. The voltage is a drop. It's it's a potential difference. It's not dissipated. It's just that the difference exists. So watch out for that terminology. These are the voltages across or over those resistors. If we want to find the current delivered to the battery, well, that's easy. I battery equals I1 plus I2. All right, we already figured that out. So I have I1, which is 2.4, and I would add on I2, which is 1.5, and so I from the battery, the current being delivered by the battery to the circuit is 3.9 amps. Okay, so that's the last part there. Let's do another example. I've picked a dual battery circuit. Notice there's 2 batteries and they're in 2 separate branches. And I said that's okay to happen. Batteries can be there. It says determine the magnitude and direction of the current through each resistor. Okay, so there's no current assigned in this circuit. So what I'm going to do is assign the currents, right? Assign one for each branch. And I look at batteries. This is the 4-volt battery, which is larger than the 1-volt battery, and it's going to be like the more dominant battery in the circuit. So I'm going to start with current flowing from it, and I'm going to call this I3 because it will go through the 3 ohm resistor over here. And this whole branch gets this current I3. I3 comes up here and it splits up. And that makes sense to me. The voltage on this battery is going to cause current to move in this direction. I'm going to call this I2 for the 2 ohm resistor. So I3 splits up into I2 and I1. And you can see I1 flows up here, around through that resistor, and back down into this junction here. Okay, so assign positive and negatives to each circuit element. There's positives and negatives assigned to this 4 volt and 1 volt battery already. And now that I've assigned the direction of the current, I can assign positive and negative signs. When I think about I3 flowing through this 3 ohm resistor, this will be the high side of potential for this resistor, and this would be the low side, so plus minus. There would be a drop in the opposite direction for the 2 ohm, and also in that same direction for the 1 ohm resistor. Okay, so I have drops and rises assigned in my system here. It says apply Kirchhoff's junction rule. Kirchhoff's junction rule, what we're seeing is I3 equals I1 plus I2. And I'm going to note here that I have 3 unknowns, which means I'm going to have 3 equations. I'm going to label this equation 1, and this is the first equation I have to relate all of the currents through each resistor. So I'm going to have to do 2 loops in order to get 2 more equations, right? 3 unknowns, I need 3 equations. So the loop that I am going to choose is, let's do the outside loop. I think the outside loop would be a good loop. Let's go around, and I'm choosing this direction because that's the direction of the current. You could choose clockwise rather than counterclockwise, and you would just have a difference in signs in your equation. It would be an equivalent equation. So where should I start on here? Let's start on this side of the battery. Let's start here and end there. So when I go around this loop, I get a rise from the 4 volt battery. So I'm going to call this loop 1 or equation 2. All right. I get a plus 4 volts from the battery, plus 4 volts. I'm going to follow it around. The next circuit element I get to is the 1 ohm resistor, and it has a drop across it. So I'm going to put a minus V equals IR, right? We're using V equals IR. So the voltage across the resistor is going to be I times R. So I'm going to put 1 ohm times I1, all right? V equals IR. V1 equals I1 R1. Okay, so I'm going to do that on the other ones. V2 equals I2 R2, and V3 equals I3 R3. So when I get down to this resistor here, notice now I have to consider V3, that's a drop, and I'm going to put in I3, R3, and I know R3 is 3. So I get minus 3 I3, and all of that has to equal 0. I did a complete loop. All of that has to add up to 0. So my 2 of my unknowns are in here, so I have 2 equations. Let's do a third one. Let's do another loop, and I am going to choose the top loop here. And I'm going to choose it in this direction. I'm going to get more positive signs than negatives when I do it in that direction. So this third loop I'm doing here, I'm going to start here on this side of the battery. I'm going to get a 1 volt rise over the other battery. I'm going to get a V2, a drop of V2 over this resistor. I'm going to put I2 R2 in there, so I'm going to put minus 2 I2. When I go up the top, notice I'm going in the opposite direction of the loop than the current in this branch. So I'm going to get a rise over this resistor. The rise is going to be R1 I1, so I'm going to put plus 1 I1. And set all of that equal to 0. I'm back to the end of my loop. Okay. So notice that in this problem, V1 is a positive sign in this equation because I went the loop from left to right for that loop, and over here it's negative because I went from right to left in the other loop. Just because you go through a resistor doesn't mean it's a negative sign every time, and that's often what they're asking you when they ask you to write loop equations, is can you get the signs right? The rest of the terms are pretty basic and straightforward. The signs can get confusing. So now that I have 3 equations, what I'm going to do is plug in I3 here, and then I'll have 2 equations with I1 and I2 in it, so that'll make it easy. I get 4 minus I1 minus 3 times I1 plus I2 equals 0. So this is just going to be a bunch of algebra, and I'll keep talking through my algebra. This can be a frustrating part of students answering these questions, is working through the algebra. I will often not put a 3 equation, 3 unknown problem on my assessments because it's not an algebra test, it's a physics test. So I may give you a value of a current and see how you incorporate that information into your analysis. Often they just have you write these equations, these 3 equations, they'll have you write those out and make you stop there and not solve the whole entire problem. But sometimes you are asked to solve the entire problem, and the rest of this, I'm going to assure you, is algebra. Only algebra. If you have it up until this point, you have all the physics correct. And so you want to be careful with your algebraic steps. Make sure you keep track of signs and do your addition correctly. So for instance here, I have to distribute the -3 to both I1 and I2. So when I solve this, I get 4 minus 4I1. I'll have a 1I1 and a -3I1. That's a -4I1 minus 3I2, and that equals 0. I'm going to solve this equation for I1. So let's solve this equation for I1. I'm going to move it over this side so it's positive and then divide by 4. So I'm going to get 4 minus 3I2 divided by 4, which is 1 minus 3/4 I2. I'm going to take that expression and plug it in here with a plus sign. So I get 1 minus 2I2 plus 1 times this expression. So I'm just going to put it in 1 minus 3/4 I2, and that equals 0. So now I just have a linear equation of I2, and I can solve for I2. I can get 2, and that's minus -2 minus 3/4. Well, -2 is -8/4. -8/4 minus 3/4 is -11/4 I2 equals 0. Okay, let's keep solving. I can get I2 on one side, then I'll have it 4/11 times 2. And so I get a value for I2 out of here just like I expected, 8/11 amps. Okay, so that is 0.727 amps when you run that through the calculator, 8/11. And when I look at I2, let's assign a direction. It wants the magnitude and direction of each current. When I do this, I see that I assigned the current to the left, and I got a positive value here. Notice I got a positive value here, positive. So that means I2 is to the left in that branch. Now that I know I2, I can plug it into this equation and solve for I1. I1 will be 1 minus 3/4 times 8/11. So I get 1 minus 6/11, and so I1 equals 5/11 amps. So I1 is also a positive value. I'm getting a positive value here, and I assigned it from right to left, so it is also going in the left direction through that branch. Finally, I3, I can take these two values. I'm going to get I1, which is 5/11, and add on I2, which is 8/11. And so I3 is 13/11, bigger than both of them. It's got a positive sign as well, so I assigned it in the correct direction. And that means it's to the right in this problem. Okay, in that branch down there, it's to the right. So those are the three answers for this problem. And notice it took a little bit of algebra, a little bit of working through the algebra clearly in order to get an answer. And that's where I see, again, students stumble on this problem, is not setting up the equations. The equations are typically pretty easy to set up. Once you figure out how to do that, you can be consistent about it. It's the solving with the algebra that can be complicated.